One of the major advantage in consistent quality you get is all the weld seams, first of all, looks identical. All the weld seams follow the required WPS PQR. You get all the jobs the same quality that you were getting on day one, and this is repeated throughout the life cycle of the machine. So that is the basic advantage that you receive. Second is higher productivity. As the overall intervention decreases, the productivity increases. Secondly, welding is a very harsh process. It takes toll on the welder. In general, a manual welder cannot weld more than, on an average, cannot weld more than somewhere 180 to 240 minutes in an 8 to 9 hour shift. The process takes a toll. The gases are corrosive. So the amount of time you can weld in a shift is limited. What happens in automation is heat does not affect the machine. Yes, it affects the weld joint. We have to always take care of the interpass temperatures, but it does not affect the machine. So the overall throughput can be increased to a span of 4 hours to 6 hours, increasing the general productivity as well as the throughput. Nowadays, as the industry was growing, mass production was the need. For mass production, the amount of welding deposition needed grew up exorbitantly. So if we take an example of L&T, L&T at present at one manufacturing complex is employing somewhere around about 15,000 welders and still are unable to reach the needed production levels. If they simply go on increasing the manpower, that would also overall increase the overheads, increase the amount of space required, and increase the capital equipment invested behind each welder. Hence, automation helps here by giving a consistent quality and higher productivity. Now, how is this automation divided? So what are the different levels of automation? First of all, whenever we think what automation is, we start with the thing that there would be a robot with 2 hands, or there would be some very sophisticated machine carrying out this process. Not necessarily. Welding are divided into different levels. You have a very simple entry level machine. You can simply keep one job on a rotary turntable, fit a torch on a holder, and rotate the job. It can weld. That is an entry level system. It solves the purpose. It gives you huge amount of productivity. But there are certain joints which have profiles, which has specific contours to be followed. That is where we go to robotics. And you even have a robotic or a custom design manufacturing line implemented for bigger components. So let's take an example of entry level automation machines. So when we say entry level machines, as I said earlier, you have simple rotary tables attached with holders, which carries out the welding joint. Here the angle setting, weld parameter setting, everything has to be done manually. The positioning of the job has to be done manually. The only thing that is negated is the welding process. You simply have to press one button, the job rotates, or the job goes in a linear motion and welding is carried out. So the first example here we'll take is of the linear welds. The linear weld tractors are majorly used in long sim welding. What is done is on a sheet, like let's say we have to do butt welding and we have two long plates which has to be butt welded. A simple tractor is fitted across the length of the joint and torch is moved in a specific direction. And the welding is carried out. It is a very simple process and not much efforts are needed into this. The second major place where entry-level automation helps a lot, increases productivity, is in shell manufacturing. The shell normally has a very big diameter. It ranges from a diameter of 2 meters to a diameter of 4 meters. In such cases, the amount of scaffolding needed for a welder to sit near a weld joint is huge and it is very time consuming. So column and boom plays a very good role here. It gives you the accessibility at higher heights. It can reach to longer lengths. And this is widely used in the industry at present. And as I said earlier, the simple rotary joints, by simply placing or fitting a job on a chuck and rotating it. This is how the entry-level automation works. The power sources. In automation, not only the manipulator, but even power sources play a critical role because the machine has to communicate with the power source. It has to transfer the parameters. It has to see whether the parameters which has passed, whether the machine or the power source is welding at that parameter or not. There are many interlocks. In entry-level automation, these interlocks normally are not present. A manual machine is coupled with such systems and a basic on and off mechanism is utilized. Moving ahead, we have robotic automation. Our today's major focus would be on robotic automation, how the cells are designed, and how the process is established. So here you can see an example of robotic automation. In this, a robot is placed on a linear track. The job is held in a chuck. You have again a positioner which manipulates the job and welding is carried out. Robotic automation is a booming industry at present. On an average in India, 2000 robots are sold simply for robotic welding purposes. The major prevailing welding process here is GMAW or MIG welding because of the process simplicity, easier to manage, and you can get high deposition speeds. The second most adopted processes nowadays is laser welding. Again, easy to manage compared to TIG welding. What happens in the case of TIG welding is you have a certain life of the tungsten electrode. You have to grind the electrode. And all these processes require manual intervention. This reduces the overall throughput. This reduces the productivity. If we observe the industrial trends, the power source manufacturers are working on their machines, increasing their machines quality such that they can replace GTAW by GMAW. There are many processes where GTAW is a compulsion, but they are trying to achieve the quality on par or at least to an acceptable level compared to GTAW. The reason behind this is automation and throughput. We will look into details for robotic automation soon. I'll be carrying forward to the next type, that is manufacturing line. So whenever you have bigger components, huge amount of weld to be deposited, industries opt for a automated manufacturing line. The prime example here, as you can see, is the shipyard industry. In shipyard, the panels are like 30 meters long, 10 meters in width. The amount of deposition goes into tons. Manipulation of the job is not possible because of such high weights. So whole assembly line or the manufacturing line is built around this panel. And automated welding with help of certain softwares, sensing mechanism is carried out. Today, we would also be looking at certain sensing mechanisms like laser sim tracker attached on a robot and touch sense. So this also would be covered later on. Any questions till now? Okay, then I'll continue ahead.
Manan, in the chat box,
Yes.
you are having one question.
Just a second. Open the chat box, just a second. Okay, what is the question is what is the range of laser wavelength? In laser welding, the laser wavelength varies depending on what is the power source used. So if you use a IPG power source, you have an X wavelength. I'll be giving you the exact numbers. Give me some time. I have the data sheet with me. And if you have a diode laser like from company named Laserline, the wavelength varies. Normally the spot size which is generated here is of the beam diameter that we say is from 2 mm to 6.8 mm in general. And the wavelength is in, okay, I'll get back to you on wavelength within, by the end of this seminar. I have the data sheets. Give me some time onto it. Any other question? Okay, moving ahead. Just a second. Yeah. So, how is a robotic cell designed? Whenever we design a robotic cell, three parameters are major: the geometry of the job, the weld joint designing, and which process we are automating. Why are this process or why are these parameters very critical? Let's take an example. If the job is very heavy and too big, the manipulation becomes equally cumbersome. It can be even dangerous because of the weight or the tonnages. In a different case, if the job is very small, manipulation becomes very hard. Let's say we have to weld a 10 mm circle. So though the joint is very small, welding a 10 mm circle is hard to achieve than welding an 100 mm circle, because the amount of precision required by a robot is higher when we have to weld smaller joints compared to bigger joints. The second part here comes understanding the welding joint. Welding can be carried out in 6G positions, or 6F positions, however we look at it. When we design a machine, the normal welding is done in 1G, 2G or 3G welding max. In case of pipe welding, 6G automation is available. But when it comes to do overhead welding by a machine, it is a tedious work and not normally opted for. And why we look at to the welding processes? Because if we have MIG welding, yes, we can play with the angles, tweak with the parameters, can achieve accessibility easily. But in case of GTAW, we have many limitations. Normally, GTAW is preferred to used in just 1G, 2G and 3G only. As filler wire comes in the weld pool, gravity plays a major role here. And controlling parameters through a machine against gravity is not simple. Hence, when it comes to overhead welding or a tricky profile contour, it is less opted. Now we will understand this cell designing through some case studies. So the first case study for today is of nozzle welding. So this was one of the projects that we carried out. Just open up the details. Okay. I'll give you a brief idea of this weld joint. So if we see this weld joint, this is a boiler joint. In boiler, it comes under ASME section 5 pressure vessel joint. The thickness varies from 25 mm to 150 mm. The welding has to pass the NDT requirement of UT as well as PT. The criticality in this weld is the profile groove. The profile design is parabolic hyperbola. So the weld is carried out in, it starts with a 2G joint position, goes to 1G, then again comes back to 2G and shifts to 1G position. So during one weld seam weld, the welding positions are continuously changing. So that is the primary concern, that how can we manipulate the robot? How can we get the accessibility for such weld joints? Because maintaining the welding angle is also critical. If we do not maintain the welding angles, what we lose here or what issues it can come is sidewall fusion, improper bead overlap. Like improper bead overlap would lead to failures in visuals. So these are the two primary concerns. In this video, we would be observing how the robot torch is manipulating around the welding joint with a given angles, what controls we have, and what tweaking we can do in a cell. So as we see here, the job, we can change the angles. That is our weld angle. The torch is fouling at present. So in simulation softwares, we check how we can negate this fouling. So during checking, we update these parameters, we update these angles. The second thing to be observed here is, as the torch is moving ahead, the job is also changing its angle. So the job manipulation and the torch movement are in a complete sync. So here, as we can see, when we approach the 90-degree position of the job is in the 1G position. When we had started earlier, the job was in the 2G position. So to have a uniform weld, we require a synchronized motion between the welding torch and the positioner. If the synchronization breaks, the major issue comes in first is in the welding speed and then comes in the positioning part. So I'll just go to the overview once again. Give me a moment. So this is how the joint looks like in reality. You have a big pipe which is rotated on a positioner. and the robot manipulates around it. The positioner as well as the robot track are completely in sync with the joint. If this sync breaks, the output goes away. The advantage here, we can weld multiple joints together in a single setup. So even if, let's say, we have an interpass reached on one joint, we can simply shift to another joint, weld there, and come back after cooling off that joint is done. As you can see here, the same joint is traversed repeatedly. So this is multi-pass welding. As we have thickness, it requires huge amount of weld passes to cover the thickness. I will simply shift to the second joint. As you can see, it does multiple passes on the same. Then, as per the programming and the setup, it automatically shifts to the adjacent joint or the pre-programmed joint. It carries out the welding. One major point here, if you have observed, during the simulation, what we checked is the robot fouling with the nozzle. So whenever during initial setup, initial check, we find such issues, we change the torch bracket, we change the torch angles and re-simulate the whole process. Once the whole process works without any fouling or accessibility issue, this torch design is then passed on to the manufacturer and the torch either is custom made or selected from their catalog. Every robotic welding torch is combined with a collision sensor. So behind this, we can see one cylinder, orange color, not, yes, I'll try to focus it up. Yes, so this orange cylinder behind the torch is a collision sensor. It triggers whenever a collision occurs. We don't have eyes here. We don't know what is happening. So we have certain safety interlock devices and collision sensor is one of them. Whenever more than certain pressure is applied on the welding torch, a collision signal is generated and the complete process is stopped. This saves torch from being twisted or bent, and it also saves from welding going onto the wrong path. So this is how the welding is carried out on the pipe. Just forwarding the video, the same motion again and again. Now we will look into how the multi-pass planning is done for this joint. Because when we have high amount of thickness coming down, we have to weld multi-passes. And this is how the multi-pass is planned. So we consider the value of the root pass and provide offsets accordingly. So here, as you can see, we have shown the root pass in the center window. In the multi-pass window, you can simply add an additional pass, give it the required offset in the direction of either base, wall, as in reference to the root pass. You can even set the layer number and the nomenclature as per the requirement. The welding parameters for every pass can be kept different. Even sectoring is possible in case of automation. So for X degrees, we can have a certain parameters. For another degree, we can have a different set of parameters being called. So this is how we plan a joint, the different passes within that joint. Normally what we prefer is to create a database and reutilize this database as many as locations or projects possible. This gives us an advantage of ready-made set of parameters and faster commissioning time. So this is how the multi-layer.
Hello, Manan, you are talking. Hello, 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 Manan. Hello, Manan. Hello, hello, Manan. Are you hearing me? Hello, hello.
Yes, sir, audible.
Audible. Manan, Manan, are you audible? Speaking or not? Uh,
Yes, sir. Audio
hello.
is okay.
His voice, speaker voice is not hearing, no?
Yeah, videos audio is not coming.
That, not speaker voice also not coming, no? He's talking or
Yes.
not? Hello, Manan? Hello, Manan. Upendra, are you hear my voice?
Yes, sir, I can hear you,
Yeah.
but I think audio from Manan sir is not there.
We are trying to call him. Okay, I think he has kept his phone.
Manan
No,
sir,
sir, no.
you are still not audible. Sure, sir.
Hello. Am I audible now?
Yeah, you are now audible. Yeah.
Perfect. Okay. Okay. I'll repeat this particular cell design. Yeah.
Little bit louder, you can talk. No problem.
Now how is the voice?
Yeah. This is okay. This pitch is okay.
Perfect, sir. Perfect.
Okay.
Okay. So, yeah, this is a specific case study of MFF, which
Your
is an oil and
presentation
gas.
is not shared, Manan.
Oh, yes. I disconnected it.
Yeah, now it is clear.
Perfect, sir. Yeah. Okay. This is an example of MFF, which is an oil and gas company. They manufacture oil rigs for offshore installations. Their major components are volumetric and big in size. And one of the WPS requirement here was that all the welding had to be carried out either in 1F or 2F positions only. So the cell that we designed here was keeping all these factors in mind. We kept the industrial robot on a linear track so that it can achieve longer welds. This welding can be carried out by a entry level automation also. So if we see a simple carriage, a carriage can move in a linear direction and perform this welding. But the advantage with robot that you get here is when we have higher thicknesses, you can program the multi-pass and this can be implemented. So higher thickness joints can be welded in a single go without any intervention. Second thing, for smaller components, we have kept a 2-axis positioner. So it has turn plus tilt option. This helps in positioning the weld piece in the desired angle. Okay, I'll be showing the video of this cell now. So this was the customer's requirement. This is what then we designed in further addition to it. And the installation looks similar to this. So the track installation was still pending. So initially when we installed the two positioners, you can see that the positioners are completely in sync. They are in control of the robot. This gives you the manipulation the way we want, the way the process demands. So this is what advantage we get through 2-axis positioners. Okay. Stopping this. Now moving forward to the some photographs of this installation. So the joints welded on this system, we can weld a descendant petal. We can achieve the angles that we want again through manipulation. A simple butt joint, rotary joints. You can weld pipe to a nozzle. So circular joint again. You can have connection details mounted on the positioner. They are similar to I-beams. The major advantage here is that all the weld joints that it be which we are seeing in the vertical direction also are carried out in 1F or 2F position by manipulating the job. certain nozzle weldolets. Yes. So one single system can weld so many different types of joints. So that is the degree of freedom and flexibility we can get within this setup. Now, I said earlier that the system is inflexible also. So if we see the previous case study, such weld joints cannot be carried out on this setup. So every setup is made as per the requirement. The advantage with a welder, they can weld anywhere needed. They are not bounded by job dimensions, job designs. They are just bounded by the WBSPQR. That's it. Okay, moving forward to the third case study is welding in closed spaces. The hardest part is to get accessibility of the joint. There are times when the joint is so far away or that a automation system requires huge amount of manipulation, huge amount of hardware, and this increases the overall system cost. So people even opt out in such cases. So reachability is a major concern when we do automation. So the first example here is welding within an
Hello, Manan. Once again, your voice gone. Hello, Manan. Hello.
So seems like he's not able to hear us also.
Huh? You're not able to hear also. Yeah. Ah, hello, Sivaram. He's once again, he's got audio. Mm. Yeah, yeah. You were there, You were there in the meeting. Okay. Okay. I thought, yeah, yeah. You please take it. Sir, now, dear participants, please, sorry for the interruption. That speaker, he's having some issue with the computer. We will wait for 5 minutes. He's just restarting his computer, and he will able to present that one. Okay. Upendra, is my voice is audible? No.
Yes, sir, voice is audible. Sir, I just
Okay.
want to make one announcement.
Yeah.
Dear participants, the feedback form is shared on the WhatsApp group. Similarly, I'm sharing now also. So you can find in the chat box, and please give the feedback for the morning session. So meanwhile, you can use this time and fill the feedback form.
So, dear participants, if you have any queries up to now, any sessions, you can able to ask also, no problem. You can just I will unmute all people. The person who want to ask, just they can type on the chat box. I will unmute them. They can ask or they can type also, no problem, no issues. If you have any other problem, general problem or technical questions also, you can able to ask.
Such thanks.
Hello. I hope I'm audible now.
Yes, sir, you are audible.
Sorry for the delay and inconvenience. I think something just went away. I'll start it. Give me one moment.
Sir, if possible, if you could increase the volume, maybe bring the mic closer to you.
Yes.
Yes.
How is it now?
It's perfect, sir. Now clear. Yeah.
Oh, fantastic. Great. Okay. So coming back to the closed.
Yes, sir. We can see your screen, sir. You can start.
Yes. Perfect. Yep. Okay. So as you can see,
Hello. Hello, sir. Manan, are you hearing? Yeah.
I think again, sir, there is some issue.
Yeah.